Have you ever noticed that modern trains, built with advanced engineering, precision steel wheels, and powerful locomotives, still tend to operate at what feels like a strangely consistent speed across much of the world? Not slow, but also not truly fast by modern standards. And what's even more interesting is this. It's not that trains are incapable of going faster. In many cases, the technology already exists to push far beyond these limits. But once you remove the train itself from the equation, something becomes clear. Speed isn't defined by the engine. Why don't most trains in the world go much faster than 120 kilometers per hour? In an age where airplanes cross continents in hours and high-speed trains can exceed 300 kilometers per hour, it might seem surprising that many of the trains people ride every day still operate at speeds close to 120 kilometers per hour, or sometimes even less. At first glance, the solution appears simple. Just build a more powerful locomotive, add bigger engines, and make the train go faster. But in reality, train speed has very little to do with engine power alone. Behind every train journey lies a complex system of tracks, signals, curves, braking distances, maintenance requirements, safety regulations, and economic realities. In fact, one of the biggest reasons trains cannot travel faster often has nothing to do with the train itself. So why can't most trains go faster than 120 kilometers per hour? Today, we're taking a closer look at the engineering, physics, and infrastructure challenges that limit train speeds across much of the world. To understand the problem, we first need to look beneath the train. Most people focus on locomotives when thinking about speed, but railway engineers often focus on something entirely different: the track. A train is only as fast as the railway line it travels on. Unlike cars, trains cannot simply steer around obstacles or adjust their path. They are locked onto steel rails that follow a predetermined route. Every curve, bridge, tunnel, and section of track imposes limits on how fast a train can safely travel. Many railway networks in Europe and North America were originally built decades, or even more than a century, ago. At the time, engineers designed them for trains traveling at much lower speeds than modern technology allows. As a result, many existing routes contain curves that are simply too sharp for high-speed operation. When a train enters a curve, passengers experience a sideways force pushing them outward. The faster the train travels, the stronger this force becomes. At sufficiently high speeds, passenger comfort decreases, wheel wear increases, and the risk of derailment rises significantly. To support higher speeds, railway lines require gentler curves with much larger turning radii. However, rebuilding hundreds or thousands of kilometers of railway track is an enormously expensive undertaking. For this reason, many railways continue operating at speeds around 120 kilometers per hour because that speed works safely with existing infrastructure. Track geometry is only part of the challenge. Another major limitation comes from stopping distance. A fully loaded passenger train can weigh hundreds of tons. Freight trains can weigh several thousand tons. At 120 kilometers per hour, a train already requires a surprisingly long distance to come to a complete stop. At 200 kilometers per hour or more, the required braking distance increases dramatically. Unlike automobiles, trains rely on steel wheels rolling on steel rails. While this combination is extremely efficient, it provides relatively little friction compared to rubber tires on asphalt. This means trains cannot stop quickly. As speeds increase, railway operators must install more advanced signaling systems that allow trains to communicate continuously with control centers and with each other. Traditional signal systems designed decades ago often become inadequate at higher speeds. Upgrading these systems can cost billions of dollars across an entire railway network. Even if the train itself is capable of traveling faster, safety regulations may prevent it from doing so unless the signaling infrastructure is upgraded as well. Then there is the issue of level crossings. Across much of Europe and North America, railway lines intersect roads at thousands of locations. At 120 kilometers per hour, these crossings already require extensive warning systems. As train speeds increase, the risk associated with these intersections rises significantly. High-speed railways often eliminate level crossings entirely, replacing them with bridges and tunnels. This dramatically improves safety but also greatly increases construction costs. Another challenge comes from the forces acting on the train itself. As speed increases, air resistance becomes one of the largest obstacles. Many people assume that doubling speed simply requires twice as much power. In reality, aerodynamic drag increases much faster. A train traveling at 240 km per hour faces vastly more air resistance than one traveling at 120 km per hour. Overcoming this resistance requires substantially more energy. That means higher electricity consumption or greater fuel usage, depending on the type of train. For railway operators, this creates an important economic question. Does the time saved justify the additional operating costs? In many cases, the answer is no. For regional routes with frequent stops, increasing maximum speed often provides surprisingly little benefit. If a train stops every few kilometers, it may spend more time accelerating and braking than actually traveling at top speed. Under those conditions, investing billions in high-speed infrastructure may not make financial sense. Passenger comfort is another important factor. At higher speeds, even small imperfections in the track can create stronger vibrations and movement. Maintaining smooth operation requires exceptionally precise track construction and constant maintenance. High-speed rail lines are often built to standards far beyond those used for conventional railways. This level of precision comes with significant ongoing costs. Weather also plays a role. Strong crosswinds, snow, ice, extreme heat, and heavy rainfall can all affect railway operations. At higher speeds, these environmental factors become increasingly important. Railway operators must account for them when determining safe operating limits. Despite these challenges, some trains do travel much faster. Countries such as France, Germany, Spain, Italy, Japan, and China have invested heavily in dedicated high-speed rail networks. These systems use specially designed tracks, advanced signaling technology, carefully engineered curves, and extensive safety measures. As a result, trains on these routes can routinely operate at speeds exceeding 250 or even 300 km per hour. However, these networks represent enormous investments that often require decades of planning and construction. For many existing railway systems, maintaining reliable service at around 120 km per hour remains the most practical solution. In the end, the reason most trains cannot go much faster than 120 km per hour has very little to do with the train itself. The real limitations lie in the infrastructure beneath it. Track design, braking distance, signaling systems, safety requirements, level crossings, aerodynamics, maintenance costs, and economics all work together to determine how fast a train can safely and efficiently operate. While modern engineering has proven that trains can travel at extraordinary speeds, achieving those speeds requires far more than simply building a faster locomotive. The next time you see a train traveling down the tracks, remember that its speed is the result of an entire transportation system working together, not just the engine pulling the cars. Thank you for watching. If you enjoyed this video and would like to see more engineering and transportation documentaries, be sure to like, subscribe, and share your suggestions for future topics in the comments below. And until next time, stay curious.